Explain to me valence electron and chemical synthesis. Valence electrons are the outermost electrons in an atom, located in the highest energy level or shell. These electrons are involved in chemical reactions and determine the reactivity and bonding behavior of an atom. The number of valence electrons an atom has determines its position in the periodic table and its chemical properties. Chemical synthesis is the process of creating a new chemical compound by combining two or more elements or molecules through a chemical reaction. This process is used in a wide range of industries, including pharmaceuticals, materials science, and agriculture. Valence electrons are crucial in chemical synthesis because they are the electrons involved in the formation of chemical bonds between atoms. The valence electrons of one atom interact with the valence electrons of another atom to form a chemical bond. By controlling the number and arrangement of valence electrons in a molecule, chemists can manipulate its reactivity, stability, and other properties. For example, in organic chemistry, chemists often use reactions involving valence electrons to create new compounds. One common reaction is called a nucleophilic substitution, where a nucleophile, an atom or molecule with a negative charge or a lone pair of electrons, attacks an atom with a positive charge, replacing one of its valence electrons with a new one. This type of reaction is used in the synthesis of many important drugs and chemicals. In summary, valence electrons are crucial in chemical synthesis because they determine the reactivity and bonding behavior of atoms, which are key factors in creating new compounds through chemical reactions. I want to know more about one common reaction is called a nucleophilic substitution, where a nucleophile, an atom or molecule with a negative charge or a lone pair of electrons, attacks an atom with a positive charge, replacing one of its valence electrons with a new one. This type of reaction is used in the synthesis of many important drugs and chemicals. Nucleophilic substitution is a common reaction in organic chemistry, where a nucleophile replaces a leaving group from a molecule. The leaving group is typically an atom or group of atoms that is replaced by the nucleophile, resulting in the formation of a new compound. The reaction mechanism of nucleophilic substitution involves several steps. First, the nucleophile attacks the electrophilic carbon atom of the substrate molecule, resulting in the formation of an intermediate compound. The leaving group then dissociates from the intermediate compound, resulting in the formation of the final product. One of the most common types of nucleophilic substitution reactions is the SN2, substitution nucleophilic bimolecular, reaction. In this reaction, the nucleophile and the leaving group are both involved in the rate-determining step of the reaction, which means that the reaction rate is proportional to the concentrations of both the nucleophile and the substrate molecule. Another type of nucleophilic substitution reaction is the SN1, substitution nucleophilic unimolecular, reaction, where the leaving group dissociates from the substrate molecule before the nucleophile attacks it. The rate-determining step of the SN1 reaction is the dissociation of the leaving group, which means that the reaction rate is only dependent on the concentration of the substrate molecule. Nucleophilic substitution reactions are widely used in the synthesis of many important drugs and chemicals, including antibiotics, antiviral agents, and anti-cancer drugs. For example, the synthesis of the antibiotic penicillin involves a nucleophilic substitution reaction, where a nucleophile attacks a carbonyl group to form a new bond and replace a leaving group. Overall, nucleophilic substitution reactions are important tools for organic chemists in the development of new compounds for various applications. Can you tell me more about SN2, substitution nucleophilic bimolecular, and SN1, substitution nucleophilic unimolecular? Sure, I'd be happy to explain the differences between SN2 and SN1 reactions. SN2, substitution nucleophilic bimolecular, reactions. In an SN2 reaction, a nucleophile attacks a substrate molecule at the same time that a leaving group departs from the substrate molecule. The reaction occurs in one step, with both the nucleophile and the leaving group involved in the rate-determining step. This means that the rate of the reaction depends on the concentrations of both the substrate and the nucleophile. The mechanism of the SN2 reaction involves a nucleophile attacking the carbon atom bearing the leaving group. The attack occurs from the opposite side of the molecule as the leaving group, resulting in an inversion of the stereochemistry. This is known as a backside attack. As a result, the stereochemistry of the substrate molecule is inverted during the reaction. SN2 reactions typically occur with primary or secondary carbon atoms, where steric hindrance is low. The reaction rate is also affected by the nature of the leaving group and the nucleophile. Common examples of SN2 reactions include the synthesis of alkyl halides, esters, and amides. SN1, substitution nucleophilic unimolecular reactions. In an SN1 reaction, the leaving group dissociates from the substrate molecule before the nucleophile attacks it. This dissociation results in the formation of a carbocation intermediate, which is then attacked by a nucleophile to form the final product. The rate-determining step in an SN1 reaction is the dissociation of the leaving group, which means that the rate of the reaction depends only on the concentration of the substrate molecule. This makes the reaction first order with respect to the substrate molecule. SN1 reactions typically occur with tertiary or secondary carbon atoms, where steric hindrance is high. The reaction rate is also affected by the nature of the leaving group and the stability of the carbocation intermediate. Common examples of SN1 reactions include the synthesis of alkyl halides, alcohols, and ethers. Overall, SN2 and SN1 reactions are important tools in organic chemistry for synthesizing a wide range of compounds. The choice of reaction mechanism depends on the nature of the substrate molecule and the desired product. Okay, tell me more about SN1, substitution nucleophilic unimolecular and synthesis of alkyl halides, esters, and amides. SN1, substitution nucleophilic unimolecular reactions. In an SN1 reaction, the leaving group dissociates from the substrate molecule before the nucleophile attacks it. This dissociation results in the formation of a carbocation intermediate, which is then attacked by a nucleophile to form the final product. The mechanism of the SN1 reaction involves three main steps. 1. The leaving group dissociates from the substrate molecule, resulting in the formation of a carbocation intermediate. 2. The carbocation intermediate undergoes rearrangement, if possible, to form a more stable carbocation. 3. The nucleophile attacks the carbocation intermediate to form the final product. The rate-determining step in an SN1 reaction is the dissociation of the leaving group, which means that the rate of the reaction depends only on the concentration of the substrate molecule. This makes the reaction first order with respect to the substrate molecule. SN1 reactions typically occur with tertiary or secondary carbon atoms, where steric hindrance is high. The reaction rate is also affected by the nature of the leaving group and the stability of the carbocation intermediate. Synthesis of alkyl halides, esters, and amides. Alkyl halides, esters, and amides are important classes of organic compounds that can be synthesized using SN1 and SN2 reactions. For example, alkyl halides can be synthesized by the reaction of alcohols with hydrogen halides such as HCl or HBr. The reaction proceeds through an SN1 or SN2 mechanism depending on the nature of the alcohol substrate. Primary and secondary alcohols undergo SN2 reactions to form alkyl halides, while tertiary alcohols undergo SN1 reactions to form carbocation intermediates that react with halide ions to form the final product. Esters can be synthesized by the reaction of carboxylic acids with alcohols in the presence of a catalyst such as sulfuric acid. The reaction proceeds through an SN2 mechanism, with the alcohol acting as the nucleophile and the carboxylic acid acting as the substrate. Amides can be synthesized by the reaction of carboxylic acids with amines in the presence of a catalyst such as dicyclohexylcarbodiamide, DCC. The reaction proceeds through an SN2 mechanism, with the amine acting as the nucleophile and the carboxylic acid acting as the substrate. Overall, the synthesis of alkyl halides, esters, and amides through nucleophilic substitution reactions is an important tool in organic chemistry for the preparation of a wide range of organic compounds. This is new to me. Explain more about amides can be synthesized by the reaction of carboxylic acids with amines in the presence of a catalyst such as dicyclohexylcarbodiamide, DCC. The reaction proceeds through an SN2 mechanism, with the amine acting as the nucleophile and the carboxylic acid acting as the substrate. Could you show me what the balanced chemical equation looks like? Yes, of course. The synthesis of amides from carboxylic acids and amines involves a condensation reaction, where water is eliminated to form the amide bond. The reaction is typically catalyzed by a coupling reagent such as dicyclohexylcarbodiamide, DCC, which helps to activate the carboxylic acid and facilitate the reaction. Here's the balanced chemical equation for the reaction. Ru plus RNH2 plus DCC conner plus dicyclohexylurea. In this equation, R represents an alkyl or aryl group, and dicyclohexylurea is a byproduct of the reaction. The mechanism of the reaction involves the following steps. 1. The DCC catalyst reacts with the carboxylic acid to form an activated intermediate called an O-acylosurea. 2. The amine acts as a nucleophile and attacks the activated intermediate, resulting in the formation of an amide intermediate. 3. The intermediate undergoes intramolecular dehydration to eliminate a molecule of water and form the final amide product. Overall, the reaction of carboxylic acids with amines to form amides is an important transformation in organic chemistry that can be used to synthesize a wide variety of amide compounds for use in pharmaceuticals, agrochemicals, and materials science. Thanks for watching. Please like and subscribe. Have a great day.